Welcome to the Advanced Introduction to Machine Learning course. This is the lecture 5, the recorded version. So we had a live version, and this is a recorded version where we cover the part of the lecture that got missed out last time. So in today's lecture, we'll be looking at feature engineering for text data. We'll look at bag-of-words model and Tf-Idf, and also talk about other models for natural language processing, such as embeddings, that are in more popular use these days. So features for text data. Here's an email excerpt. Congratulations, you've been selected for our special offer. So let's say the context is that we want to do spam detection or classification. And we want to extract features from here. For instance, there is congratulations, that's a feature. The special offer, this is a feature. So I want to see how do I extract features from a sentence so that whenever a model sees this word congratulations, or it sees a combination of words, special offer, it triggers something that can say that this is a spam. So the question is, how do we convert strings of text to features that we can use? One of the most common starting points for natural language processing is the bag-of-words model, right? Okay. So what's a bag-of-words model? A bag-of-words model is a model that can represent string in terms of a long vector of words um, within a given vocabulary, so that only a few elements in that vocabulary are active, which is the words that are pertaining to a sentence. So you can also say it's a sparse vector representation. So what's a sparse vector? So here's a sparse vector, 0, 0, 0, 1, 0, 0. So this is a sparse vector. And this is in comparison to a dense vector. So dense vector of the same dimension would look like 0.4, negative 0.5, 1, 2.3, negative 4.7, and maybe let's say 8. So this is, both of these are in 6 dimensions. But you see, it is sparse because there are a lot of zeros. So bag of words is kind of a sparse representation. That is, there are a lot of zeros because those words in the vocabulary do not exist in a sentence. And you only have ones or some other float value at places where the words do exist in the sentence. So this is also called a one-hot encoding in this case. One-hot encoding because there's only one of them that's hot. But you can think of bag of words model, bag of words, as a multi-hot encoding. Why multi-hot? We'll see that in a bit. But it's a natural extension of one-hot encoding. So let's take an example. So let's say there are 3 sentences. This is a simple sentence. The second sentence was how about this one, and sentence 3 is one more. So if you look at the vocabulary here, vocabulary is the set of all words. So in this case, we have 3 sentences. So 3 sentences give rise to a vocabulary that has this. It has, so as I was saying, the vocabulary here based off these 3 sentences will give you these words. This is a simple sentence. How about, this is already accounted for, so this shows up twice, right? And then 1 also shows up twice. So we're only going to add it once. So vocabulary is a set of unique words in a set of sentences or in a set of documents. So how about this is accounted 1, 1 is again accounted, and then we have more. Okay, so here the vocabulary size that is the cardinality of the set V is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 words. If you think of these 3 sentences as your document base and you're building a vocabulary from your documents, then we get 9 words in this vocabulary. So now what we're going to do, let me call this vocabulary from 3 sentences. Okay, so now what we're going to do is we're going to take each sentence and represent it in terms of the vocabulary using the bag of words model. Okay, it is very simple, it's very intuitive, and you'll see how easy it is to understand bag of words. So let me just put in all the words here. So this is a simple sentence. How about, let me also put 1 here. So notice the order doesn't matter so much, but having a good representation here is important. So let's start with sentence 1. All right, so let's look at how it's represented. So sentence 1, there is a this, so I'm going to put a 1 where I see this. There's a is, so that's a 1. A, yes, there's a 1. Simple, yes, there's a 1. And sentence is a 1. Everything else is 0. Am I missing something? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. More, I guess there's the word more that's missing. Let me just add more somewhere here. Okay, so this is 0. Now sentence 2. How about this one? So how, I see how here, 1, about 1, this is 1, and then 1 is 1. Everything else is 0. Okay, then S3 is 1 more, so 1, then more is here, 0, 0, 0, 0, 0, 0, 0. So you see, this is each of these 3 sentences is a multi-hot encoding. Okay. Okay, so each of the 3 sentences below can be represented as a multi-hot encoding bag of words. So we see why it's a bag of words, because we have a bag of words here. The vocabulary forms a bag of words, and you represent each sentence as a sparse multi-hot representation in this bag of words, where you have many zeros and you have ones that indicate the words. So it can happen that you have a sentence that has more than one word. So you have a word that's repeated. In that case, it's a modeling choice in the bag of words model to either count a word once or count it based on the frequency of its occurrence. So we'll talk about term frequency in a bit. So you can work with these bag of words model. You can tweak it based on frequency. You can normalize it. But the basic idea is capture all the words that show up in a sentence or in a document in terms of the vocabulary through this bag of words multi-hot encoding, which is also sparse. All right. So that's one of the most fundamental ways to represent sentences and documents. And this is also, turns out, the starting point for what we'll learn probably in the next lecture, which is on embeddings. So a lot of embedding models start with bag of words, and then they get dense, compact, concise embeddings, right? So the disadvantage of a bag of words model is, imagine you have 300,000 words in your vocabulary and your sentence is only 10 words long. You're going to have 10 non-zero elements in this 300,000 long vector, which is a very inefficient representation. But even if you're efficient about how you represent your sentence, when you do training using a deep learning model, you still have to put in all these words in your input layer, and that's going to increase your the parameter size, right? So it's 300,000 times the hidden dimension. So that's going to really, blow up. And so there is a need to have more compact and concise representations, which a lot of embedding models do. And they provide embeddings, contextual or non-contextual embeddings. But the starting point for many of these embedding models, or even pre-training models, would be coming from bag of words. So very fundamental concept to understand. All right. So most of you by now, if you're seeing the video right now, you might have already taken a look at assignment 2 and gotten started with it, or even had a result on Kaggle contest related to this. So some of the data pre-processing that you may want to do include removal of stop words. So for instance, the, a articles or other filler words may not actually contribute to the prediction. So there are libraries in NLTK that can, the Natural Language Toolkit, NLTK, that can help you with stop word removal. Also, you can remove punctuations if it doesn't help. So there's some pre-processing that's specific to NLP, or let's call this natural language processing. And yeah, so it's removal of stop words, could be found in NLTK library. So there's like modules that can help you do this. So for instance, what's an example of pre-processing? So we have a sentence, let's say a spam sentence. Congratulations, you've been selected for a special offer. Maybe after pre-processing, you have something that looks like this: congratulations, and we remove the exclamation mark, have been selected, our special offer. So kind of removing some of the other filler words. But sometimes you may not want to do this pre-processing. For instance, with spam emails, we do know if you're using exclamation marks and drawing attention to a certain sentence through punctuations, that might be an indication or a feature that it is spam. So this is a pre-processing that you can apply to sentences, but depending on the task, for instance, spam filtering, you may not want to apply this specific punctuation filter because it plays a role in detecting if a sentence is spam or not. All right. And after pre-processing of the sentence, bag of words can be used to vectorize. So vectorize is putting a set of words into a vector through the bag of words representation. So remember, a sentence is a set of words. It doesn't have any numbers, or it's not a numeric type, right? It's not a numerical attribute. But once you use the bag of words model, you know each dimension represents a word. So the vector itself is numeric because it tells you the presence or absence of words. So you've taken a sentence and converted into something that is numeric and has a set of numbers. And as we know, machine learning is something that works with numbers, right? So at the end of the day, you have to represent things as numbers, and bag of words helps us do that. Okay. So bag of words is definitely looking at linear features, which is take look at a presence or absence of a word, right? So let me write that down. Presence or absence of a word in bag of words. So sometimes we call it BOW, B-O-W, bag of words model. This is a linear model, right? But sometimes or oftentimes you may want to capture nonlinear things. For instance, in sentiment analysis, so here, let me just spell this out. Bad indicates a negative sentiment, okay? But not bad indicates a positive sentiment. So bad is an example of a unigram. So unigram are single words or single units. So the units could be words, it could be stems, so it could be characters, but here like, we're looking at words. So unigram refers to single words. So if I'm looking at single words as features in my bag of words model, that's a unigram. So detecting the presence or absence of bad, that tells me there's some negative sentiment going on. But hey, wait a minute. If I have not bad, so this is a bigram because I'm combining not and bad. So that's bigram. Now it's a positive sentiment, right? So two words combine. So when I look at a bag of words model, I might have something like, so let's say I'm looking at a vector. I say, okay, here's bad, here's good, here's not bad. So I'll say it's not underscore bad. So I'm going to have a one here. I'm going to have one for bad as well, because bad as a word is present in the sentence, but not bad is also present. And this is probably going to be, this is a non-linear feature that is actually telling me more about what's going on in terms of sentiments in the sentence. So for sentiment analysis, using nonlinear features such as bigrams is very useful. And you can think of this extension of bigrams and unigrams as what people call n-grams. So n-grams, n is equal to 1, it's a unigram. N is equal to 2 bigrams, and so on. You can have an n-gram, so n equals 3 or n equals 10. So then you're looking at combination of words showing up in exactly that order in a sentence and the presence or absence of an n-gram, right? So you're not just looking at a presence or absence of one word, but you're looking at presence or absence of a set of words in a specific order that gives you some meaning or some interpretation for a prediction like sentiment classification. All right. So we spoke about n-grams. Let's now look at an in-class exercise on bag of words. So let's say you have 1,000 sentences in a document. So you have a document, all right? So that's a document. And you have 1,000 sentences. And let's say in this document you have 6,723 words, of which 5,000 are unique. For instance, you have a word the or a that gets repeated more than once. Then you kind of collect the unique number of unique words and you get 5,000. So the question here is, for the bag of words model, what would be the dimension of the vector that represents each sentence in this document? So you're collecting a vocabulary from this document. You're designing a vocabulary from this document and using that vocabulary to represent every sentence in this document. What would be the dimension of the bag of words vector for each sentence? Okay, so maybe take a minute to think about this, process the information, and then think about your choice. Feel free to pause this video as you answer this question, and then we'll come back. All right, so hopefully you thought about this and you paused the video, you thought about it. So the answer is not 6,723 because those do not have unique words. So the number of unique words is also the size of the vocabulary. like we looked at an earlier example on backward. So that would be here, right? Here's a question for you to ponder on. I do training on a backward model that sees a certain vocabulary, let's say 5,000 words. Now, during testing with sentiment analysis, I might encounter a word the model has never seen before. Okay, so how do we do with out of vocabulary? So this is called out of vocabulary. How do we deal with out of vocabulary words that show up during test time? What would you do in this case? So I'll leave that for you to ponder on, but one easy thing that you can do is to just ignore. I've not seen this word, so I'm going to ignore it, right? But there may be better way, but that word that you've not seen in the test set that you're ignoring might actually convey useful information for you to make a prediction. So maybe there is something better than doing just ignoring. We'll probably take a look at this when we go into more details later on. So, but I would leave this as an exercise for you to think about. So easy baseline. So baseline refers to like the starting model. So easy baseline here is to just ignore out of vocabulary words during prediction or inference. So inference is just another name for prediction. So out of vocab. Okay, so our next concept that is connected to backward words and leads to a better representation than backward words for many tasks is something called term frequency and inverse document frequency. So Tf-Idf stands for term frequency, inverse document frequency. So Tf-Idf is essentially a scoring of a given word within a document Y. So it's telling you how much importance should I place on a particular word in a given document. So there's a very easy way to determine this. So let's say there's a word here, and so this is referring to the this is referring to the weight, Tf-Idf weight, and this is the word, and this is the document. So the term frequency inverse document frequency of a given word. So if you didn't use Tf-Idf, you might just say this word is present, so let's put a 1. This word is not present, so let's put a 0. But Tf-Idf is placing more emphasis on words that are important and less emphasis on words that are not important, right? So the term frequency is the number of the frequency of a word showing up across in a given document. Or this document can also be a sentence, right? It can also be a sentence. And so that's straightforward. If I see a word apple show up in a sentence once, my TF for that apple is going to be 1. If I see it show up twice, then for my TF for term frequency for the apple in that sentence is going to be 2. So TF is straightforward. The second one is the inverse document frequency. So this is TF and this is IDF. So IDF is, so if you just kind of parse this, it's inversely proportional to the document frequency. That's why the IDF, inverse document frequency. So as you can see, this is proportional to 1 over document frequency. So this is inverse, right? There's an inverse relationship here. So why is this weighting scheme important? Well, if a word shows up very frequently in the document, maybe it's not so important. Maybe it's something that, so it could be that so here we're actually looking at not just one document, we're looking at multiple documents. So let's say I have 10 documents and a word shows up across these 10 documents. Either this word is important and the topic of these documents is the same, like they're all, let's say you're talking about politics, then you're going to see like White House or Republican or Democrat show up in all these documents. So either it's the case that the word is actually something important and something relevant to the topics that these documents share, but in a more realistic scenario, when you have a very large database of documents that could represent different topics, uh, different documents will have different words that are emphasized. But if a word is consistently showing up across many different documents of different topic types, it might be filler words or words that are not so important, like the, or things that frequently get used in sentences but don't have immediate relevance to the topic of concern for a given document. In that case, the IDF component goes down, because the IDF is inversely proportional to the document frequency. So inverse document frequency. So you see a word show up multiple times in many different documents, then you probably don't want to put a lot of weight on it. So that's what the inverse document frequency is doing. The only thing is you also have a logarithm in front of it. So there is a down weighting, but it's not like inversely proportional, but it's inversely proportional in a logarithmic sense. So there's a slightly lower down weighting in a logarithmic sense. Okay. All right. And there's also a scaling here. N is the number of total documents in which you're looking at inverse document frequency. So let's look at some examples. So we looked at spam classification. You could have different sentences. So could you please respond by tomorrow? This is not spam. Congratulations, you have been selected as a spam, and so on. So I can think of sentences as documents. So this could be document 1. This could be document 2, document 3, and so on. So sentences are not really documents, but for the purpose of an example, we can think of sentences as documents. So I can say, what is the Tf-Idf of the word you? So this is my X in email 1. So this is my Y. So this is document Y. So this is document 1, right? So the first email is like a document, and I'm saying what's the frequency of you in this? So the term frequency is 1. What is the IDF of you? So IDF is how many times does the word you show up in other documents, in this case, other emails. So here we see 3 emails. So N is equal to 3 emails. And the document frequency of the word you is 2, because it shows up in 2 of these 3 emails. So the inverse document frequency is log of N over DF. So that's log of 3 over 2. So the Tf-Idf in this case is log 1.5. Okay. Let's look at a different word, presentation. Okay. So the term frequency of presentation, this is my X. In the email 3, this is my Y, the document. The term frequency is 1. So it shows up once in this document. The IDF of presentation is log of N over document frequency of presentation. So presentation only shows up in the 3rd email. It doesn't show up in the 1st or the 2nd email. So this is log of 3 divided by 1, which is log of 3. So you notice this has a higher emphasis. Presentation gets a higher emphasis through the inverse document frequency as compared to the word you. So you'll see the Tf-Idf of presentation is log 3. So this tells us, just to summarize, that Tf-Idf of presentation is greater than the Tf-Idf of you. So that means presentation is more important as a word in this document as compared to, or in this email, as compared to you or your, right? So just the presence of you or your is not really indicating if it's spam or not spam, but something else might indicate if it's spam or not spam. So Tf-Idf is a way to fine-tune the weights that you associate with words in the bag of words model. Right. So let's look at another in-class exercise. So let's say we have 3 sentences. The first sentence is, are you in Seattle right now? The second sentence is, what's the time right now? The third sentence is right. That doesn't sound right. Okay. So if you use a Tf-Idf filter, which word is most likely to get eliminated from any of the sentences? So which word will likely get eliminated? The one that has a smaller term frequency, inverse document frequency. So Tf-Idf can be used as a filter. You can use it to filter out words that have a low Tf-Idf score, so it's not so important for the prediction, so just kind of filter it out. You can have a threshold, and you can filter it out based on that. So this question is pertaining to that. So maybe take a minute. What I would suggest is look for words that show up across different sentences more than once. So you see it in this sentence, you see it in that sentence, and calculate its Tf-Idf. And maybe if you have other candidates, then also calculate their Tf-Idf, and you'll notice one of them stands out as having a low Tf-Idf, and that's the one you will probably filter out. Okay, just take a minute to look at this. All right, so hopefully you had a chance to look at it. So which one kind of stands out? I think if you notice, right is showing up in all the three sentences. So for right, the TF in any sentence, most sentences, well, I think TF, let's look at TF if sentence 1 for right. Actually, maybe there's a better notation here. Okay. So TF of the word right in sentence 1. So right shows up once, so that's 1. The IDF of right, so this is not for any sentence, it's across sentences, is 3, because right shows up in sentence 1, sentence 2, and sentence 3. So the Tf-Idf of right in sentence 1 is log of n over df times df. So this is log of 3 over 3 times 1, so you get 0. If you take the Tf-Idf of any other word in any other sentence, you're going to get something that's non-zero, so something that's larger. So Tf-Idf of this word right is the lowest, so it's most likely to get eliminated, right? So even I'm saying right a lot of times, so it's a filler word, so I don't want to see a filler word show up for a prediction, so that it makes sense that you would want to eliminate right. Okay. So we kind of at the end of today's recorded lecture. So we'll going forward, we'll also talk about scalable representations and embeddings for sentences that are more compact and convey more information as well. It's a phenomenal and very exciting field in machine learning, which is embeddings and representation learning. So you'll see these words show up in literature as well: representation learning. And there's an entire conference for it. So I think the conference is ICLR, International Conference for Learning Representations. Also embeddings. So essentially take a large representation and make it more compact, so it can be reused. You can train more compact models. It conveys more information. So that's what representation learning is all about. So why is it important? Well, let's say you have 1,000 documents and each of them have 1,000 sentences, and each sentence has an average of 5 words. This gives us 1,000 times 1,000, that's a million, times 5, which is 5 million words. And let's say among these 5 million words, you have actually 300K unique words, might be even smaller, but let's say you have 300K unique words. So bag of words representation is going to have, for every sentence, if you want to represent a sentence, it's going to have a dimension of 300K, because that is your vocabulary size, right? So in this case, vocab size, which is the cardinality of V, is 300K. So we're going to have a 300K dimensional vector, right? So really huge vector. So this makes it computationally cumbersome to store these huge vectors or pass it into a machine learning model. It's also memory intensive. Maybe you have better ways of storing it, but still you have to work with really huge parameter spaces. So sentence embeddings comes to the rescue. So you can learn low dimensional, like 256 or 512 dimensional features. So instead of having 300K, you would have something in 256 dimensions. This is a more dense or compact representation for a sentence. Some examples that help us learn these sentences, like word-to-vec embedding, glove embedding. These are non-contextual embeddings for words, and which you can combine in a sentence to get a sentence embedding as well. So these embeddings are learned from data and are a more concise and scalable representation of sentence, right? Than what you could imagine with bag of words model. So we start with bag of words model. We said how it's helpful in encoding sentences. It gives numeric representation, but there is inefficiencies that's associated with bag of words model. And so you would want to move towards more dense and compact representations that we call embeddings. How do we get these embeddings, and what do they represent, and what do they mean, and how do they get used? We will take this forward into the next lecture. So to summarize, actually, this is coming from the last lecture. We looked at feature engineering for spam classification. We looked at bag of words model. We looked at Tf-Idf. So these are some things we touched upon in this lecture. So that's it. Hope you had a good view of this recording, and we'll hope to see you in the next lecture or next lecture recording. If you're on YouTube, feel free to follow the channel that we have on this, and we'll keep you posted with new videos. All right, see you. Bye.